Hey, Science 30s, and welcome to the first of two discussions on topic 4.1 of Unit D, harvesting nuclear energy. Today, I want to introduce you to nuclear chemistry and radioactive decay reactions. And then in my next or second part of this topic video, I'll be discussing the practical applications of these reactions and how they can be used to make power in nuclear power plants, how they can generate electricity for humans if used properly. So to start with today, I want to do a recap on the atom. Again, this should be nothing new to most of you, but again, just to kind of set the stage, atoms are comprised of three subatomic particles, as you should know. They're comprised of protons, which are positively charged, neutrons, which are neutrally charged, and electrons, which are negatively charged. The protons and the neutrons are found in the nucleus of the atom, which has most of the mass of the atom. And because they're both found in the nucleus, these two subatomic particles are given the collective name nucleons. That is a term you may not have heard before. But a nucleon refers to either a proton or a neutron because they're found in the nucleus of the atom. And then, of course, the electrons are in either clouds or orbital shells, depending on whether you subscribe to the Bohr model or the Schrodinger model or whatever. But they're not in the nucleus. For our reactions today, we're going to be discussing all three of these subatomic particles because they all do play a role in how we calculate and balance these reactions. Okay, now moving on. So again, I mentioned that the protons and the neutrons are what we call nucleons. You may know a couple of other terms, and this to be familiar all the way back to grade 9. You may remember something called the atomic number of an atom, and this is something that all of you hopefully will know if you're looking at a periodic table. And be aware your periodic table, which I don't have in front of me, hang on. The periodic table is going to come in very handy in this unit, and again, remember you do have a periodic table in your data booklet. It's on pages 6 and 7 of the data booklet. You will need the periodic table for these types of questions because you're going to need to know different elements and how many protons they have and such. So this would be probably one of the major times in this course that you're going to be referring heavily to the periodic table if you haven't been already in earlier parts of our discussions of chemistry. So anyway, see, atomic number refers to the number of protons that are found in the element, and again, every element here on the periodic table has an atomic number, and it is listed right here at the top. There it is. Number 5 would be boron. Number 6 would be carbon, 7, nitrogen, etc., etc. But that's your atomic number. Then you have something called the mass number, which is a little different than if you remember from your earlier science courses or chemistry courses, the atomic mass. The mass number is the combination total of your nucleons. So let's say, for example, I've got carbon, which has an atomic number of 6. And that carbon I now know has 6 protons because it has an atomic number of 6. I also discovered that carbon atom has 6 neutrons as well. Well, the mass number for that carbon would in fact be 12. That would be the mass number of that atom of carbon. But you'll notice something. On your periodic table, it doesn't show you the mass number. It shows you the atomic mass. And you'll notice that the atomic mass for carbon is 12.01. It's slightly off. The question is why? Why is that number not exactly the same? Why is the atomic or the atomic mass different than the mass number? You might remember this, you might know this, think about it. I'm going to give you the answer right now because it's on the next slide. Basically, what that 12.01 refers to is an average of all the different forms of carbon. Not every form of carbon has 6 protons and 6 neutrons. There are, in fact, 12 different versions of carbon. These different versions that have different mass numbers are called isotopes. And for example, carbon has 15 isotopes ranging from the smallest isotope being carbon 8, which means that it has 6 protons and 2 neutrons, all the way up to carbon 22, which has 6 protons and 16 neutrons. You will notice something, that all these different isotopes of carbon, the proton number doesn't change. It can't. If I change the number of protons of carbon, if I add a proton to carbon, it's no longer carbon. If I add a proton, I get nitrogen. Right? If I subtract a proton from carbon, it's no longer carbon. So if I want to keep an isotope of carbon, what changes in the different isotopes are the number of neutrons. Just like when you have ions, and you've talked about ions before, I'm sure, you're not changing the number of protons in an ion, you're changing the number of electrons, right? Or sorry, you're not changing the number of protons you're not changing, you're changing the number of electrons to get the different charges, whether it's sodium plus one would be essentially sodium, which would have normally 11 protons and 11 electrons if it's an atom. But if it has a charge of plus one, I've removed one of my electrons, so now I've got 11 protons and I've got 10 electrons. And the same thing works for isotopes, is that your protons don't change, your neutrons will change. So that's what an isotope is. An isotope is basically all the different versions of an atom that have different, of the same element that have different mass numbers. And some of these are going to be more stable than others, and we'll get to that in a second. There are some isotopes of carbon which are way more stable than other forms of carbon, and that's going to lead to what we'll get to in a couple of minutes here. That's going to lead to our radioactive decay reactions, which I'll get to in a couple seconds. But basically, now that I've got the information about mass number and I've got my atomic number information, I can write down something called nuclear notation. And this is probably something you haven't done before unless you've specifically done a unit on nuclear chemistry at some point in the past. This is something that's new. So what I've got written down here, and it's in your notes right here, very clear as day, I've got this notation that I've got my X as my big letter, then I've got a superscript A and I've got a subscript Z that are in front of the X. Well, what does each of those letters represent? Well, the X represents the symbol of the element. So let's use carbon. We just talked about carbon 12. All right, it had 6 protons and 6 neutrons. So the X in this case would become a C. Right? So because it's carbon, I know my symbol for my element for carbon is a C. Now, I've got a Z and an A designation here. Okay, well, the Z indicates my atomic number. Well, I know the atomic number of carbon because it's on my periodic table, as I showed you already, right here on page number 7. My atomic number for carbon is going to be 6. And again, my atomic number is equal to the number of protons. So in this case, Z becomes 6. The top number is going to be my mass number, which is going to be my number of protons plus my number of neutrons. So in this case, what was originally Z, I'm going to add Z plus my number of neutrons. Well, if I have carbon 12 in this case, I have 6 and 6, right? So it's 6 protons, 6 neutrons. So A is going to represent my mass number. So there's my nuclear notation for carbon 12. So it would be basically my symbol of my element, and then I'd have the two number designations in front of it to indicate my mass number on the top, my atomic number on the bottom. Excuse me. Choking on nuclear chemistry here, people. Don't swallow the air. Radioactive already. So basically, you've got 2 numbers here, and these numbers have to be indicated in front of each of the elements that you've got on your equations, as I'll get to in a couple seconds here. And these numbers are the ones that we're going to have to balance in our reactions. We're going to be looking at balancing these numbers out to make sure the equation is balanced. We're not dealing with necessarily coefficients, although there could be coefficients in these equations. We're not going to be really dealing with coefficients like 2 carbon 12 6s. We're dealing with our mass numbers and our atomic numbers. And in the end, on both sides of the equation, I can't lose or gain any protons or neutrons. It has to be the same number of neutrons on both sides of the reaction. There has to be the same number of protons on both sides of the reaction, and that's what we're going to be balancing out. So these equations might look a little weird, but they're actually pretty straightforward to balance once you kind of get the hang of it. Okay, so that's sort of our introduction. Oh, and a couple of other things. Using a designation as well, if we have a proton would be listed as P11. So P11 would be a designation for a proton because it's got 1 proton. That would be essentially a proton as a single proton. And it's got no neutrons with it, so it would be 1, 1. That would be a proton's designation. A neutron, on the other hand, if I had to designate a neutron with this designation, is going to be 0, 1. So my neutron would be N, and you see I'm using small letters here so we don't confuse this with nitrogen or phosphorus. They're small p, small n. So in this case, I've got I've got an atomic mass of, atomic number of 0 because there's no protons, but I do have a mass number of 1 because I do have 1 neutron present. And finally, if I have an electron's kind of the weird one. Electron has a negative designation for the atomic number because it's the opposite of a proton. So in this case, I would have a -1 for my bottom value, and my top value would be 0, just flat out 0. But those are your designations. If you see, and again, it's also on the bottom of the page here, but you'll see those because in these radioactive decay reactions, quite often you're going to see releases of either neutrons or protons or electrons, and then you have to basically jot them in to into the equation. If you also look on page, number 8 of the data booklet, it also gives you the designations on the top of the page there. You got neutrons, protons, and beta particles, which are your electrons, which I'll get to in a couple seconds. So the designations are all there in your data booklet. So again, you don't have to memorize them, but you should be familiar if you see them in these equations. All right. So how do we get radioactive decay reactions? Well, again, when these atoms are held together, they're held together with some of the strongest forces in the universe. And we talked about this already in the last unit with electromagnetic energy unit. We discussed the strongest force in the universe is strong nuclear forces. They're very, very short distances. They are held together at a microscopic level. But these are the most powerful forces in the universe. However, in some cases, if an atom decides to arrange itself into a particular isotope configuration, some isotopes are not as stable as others. So some isotopes will actually undergo radioactive decay reactions where they'll actually begin to break down at a nuclear level. They may release neutrons or electrons or photons they can release, or what are called alpha particles, which we'll get to here in a second. So these reactions will basically happen at the nuclear level. And when these happen, that's going to release radiation. So these radioactive decay reactions will release various amounts of radiation. And some radioactive decay reactions are not as harmful to radiation as others. But we'll discuss there's 3 types of these reactions we'll be discussing. And they go sort of up. They start off at the lowest amount of radiation, and then eventually we get to the most powerful radioactive decay reactions, which release the most amount of radiation, which are most damaging to living creatures, which would be your gamma decay reactions. And in a lot of cases, when these reactions occur, you're going to basically see what's called a transmutation. You're going to see carbon, for example, is going to convert itself into another, not just another isotope. It could convert itself into another isotope, but it could also convert itself into a whole other element. So it might gain a proton or lose a proton in the process, and by doing so, it actually becomes another element. So carbon, if it gained a proton, for example, in one of these radioactive decay reactions, it would actually become nitrogen, an isotope of nitrogen at that point. And let me explain how this all works together. Okay, so that's sort of the preamble for nuclear chemistry. Now let's discuss the main event for today's topic, which are your 3 radioactive decay reactions. Well, you've got 3 of them, as I mentioned. They're alpha, beta, and gamma decay reactions. We'll start off with alpha. They're the least damaging radioactive decay reactions out there. The radiation that's produced by these alpha radiation can be stopped by even something as thin as this could stop it. If I had an alpha decay reaction, this paper would be enough to stop any radiation that was coming off of an element that was radioactively decaying with an alpha reaction. Aluminum foil, even a few centimeters of air. If you're separated from the isotope by even a few centimeters, you're not going to get these alpha radiation particles getting in contact with you. So very minimal the damage that this radiation is. But what is an alpha decay reaction? Well, an alpha decay reaction is named after the particles that it releases. So in an alpha decay reaction, an unstable isotope is going to release what are called alpha particles. And alpha particles are essentially helium isotopes. They're basically releasing helium-4 is what they're releasing. Again, the isotope of helium, if I say helium-4, the helium-4, the 4 indicates the mass number. So if I said to you, it's carbon-12, then you know that the 12 is the mass number. And then from the mass number, I can actually deduce the number of neutrons that are basically being that are in that isotope by essentially taking my mass number and subtracting my atomic number. So if I take 12 minus 6, I know that in that isotope of carbon, there's going to be 6 neutrons. So I can easily deduce the number of neutrons by just having a mass number or an isotope number. So in this case, I've got helium-4, which is being released, which is listed as 42He, which would be the nuclear notation for it, or sometimes you'll see it written as 42 with the alpha symbol there. That's the alpha symbol, the Greek alpha symbol. Again, if you're not sure about this this type of reaction, there's your alpha particle right there. 4,2 helium or alpha. Sometimes you just see it listed as alpha, not the 4,2 alpha, but alpha or 4,2 helium would essentially be the same thing. So what's happening here? So essentially what's going to happen is we're going to have element X or isotope X that's going to have a mass number of A and an atomic number of Z. It's going to become a brand new element, which will become Y. Now, why is that? Well, because my atomic number is going to decrease by 2. The reason why is, if I've got, let's say, carbon, I've got carbon, let's just use an example here. I'm going to use my old carbon-12 here. So here's carbon-12. Let's put carbon-12 into my equation there, okay? So I know that if I have a radioactive decay reaction that's an alpha decay reaction for this element or this isotope, it's going to release helium. So essentially part of the atom is going to get split away from itself. So this atom is essentially losing a combination of 2 protons and 2 neutrons because we're losing 4. Because here I've got two protons that are here. I got a mass number of 4. So I know that this helium has 2 protons and 2 neutrons. So I have to factor that in to what's left over in the atom. So if I take my symbol, my number 12 here is now going to be 8, and that number is going to be 4. You see how I've balanced that? So I've got now 12 equals 8 plus 4, 6 equals 4 plus 2. That's how you balance these reactions. You have to balance the bottom or the mass. You have to balance out the atomic numbers so that this number here equals the total number of those atomic numbers on the other side of the equation. My mass number on this side has to equal the total number of mass numbers that are shown on the other side of the equation. The question now is I've got 8, 4. Well, what element do I have? Well, now I've got to go into my periodic table, and this is why I said the periodic table is very important when it comes to these equations. Well, I'm going to look for an element that has an atomic number of 4. There it is. It's beryllium. So I know that this substance that's going to be left over is essentially going to be beryllium-8. So in this case, I have balanced out my alpha decay reaction for carbon-12. It's going to produce beryllium-8 and helium-4. And remember, the helium-4 is essentially the alpha particle. And you could also write the equation as alpha, but you can see the advantage of writing it out as 4,2 helium because that allows you to balance the equation a little more easily. But if you see an equation where all you see is the alpha symbol, you have to remember the alpha symbol represents 4,2 helium, so that way you would know that you'd have to jot that in there in order to balance out the equation. So that's an alpha decay reaction. Here's an example of one. If you haven't, don't flip the slide yet if you haven't already. I'm going to give you an example here. I've got americanium, which is down here on the periodic table. There it is, americanium. And it's going to be americanium-241. It's going to undergo alpha decay. What are the products going to be of an alpha decay reaction of americanium-241? Pause me if you need to. Here we go. Ready? Well, what I'm going to do is I'm going to write my equation down. So I'm just going to write down my americanium here. So I've got americanium, which I know has an atomic number of 95. And I've been given the isotope number, which is 241. So there's my symbol. There it is. I'm going to start off with my reactant. I now know that 241 has to equal blank plus 4. Well, that's going to be 237 there for that one. And then 95 subtract 2 is going to give me 93. So I'm going to have a 93 over 234 isotope, 93 on my periodic table. If I look very carefully, apparently I'm not looking carefully enough. 93, why can't I find it on my periodic table? There it is, it's Neptunium. Neptunium is what I'm going to wind up with on that one. And again, I've given you sort of the whole Cole's Notes version here on the page. You'll look through it if it didn't make sense what I wrote on the board, but that is going to give you a breakdown of how that works. So eventually what we're going to wind up with is we're going to find out our missing element. There it is at the bottom of the page. I haven't prepared this ahead. I'm just doing it on the board. My missing element is going to be the 237 Neptunium that has the 93 atomic number, because that's the atomic number of Neptunium. And remember, it's always going to be with a alpha particle if it's an alpha reaction or an alpha decay reaction. All right, let's look at the next one. Beta decay reactions. Beta decay reactions are going to release, well, go figure, beta particles. Now, beta particles are essentially electrons. They're just releasing electrons in these reactions. So in this case, I am going to have an X element that will become a Y element. Now, why is that? Well, because we are in fact changing the, we are going to change the atomic number again, right? Because we know that if we have a -1 here, this number here has to be 1 higher than that one. Or sorry, it has to be, did I do that right? I've got this one down wrong. Let me just, let me change this. That's what the equation has to be. Had it wrong on the board. I know this atomic number has to be 1 higher, sorry, has to be 1 lower than this atomic number here, because I have an electron here that has a -1 that's going to, it's going to throw off our balance a little bit. So let me give you an example here. Let's use the carbon as an example again, my carbon 12. So I've got carbon 12 over here as my starting point. I know my carbon is going to undergo, in this case, beta decay. So I know I'm going to have on my product side, I'm going to have an electron that's going to have a -1. So I do need to balance out my atomic numbers on both sides of the equation. Well, what plus -1 is going to give me 12? In this case, what plus -1 is going to give me 6, because that's on the bottom, that's the bottom coefficient. I know this is going to have to be 7. That's going to have to be 7. What plus 0 is going to equal 12? Well, in this case, my neutrons haven't changed at all. I basically have 12 on top. So in this reaction, we're not seeing both my neutrons and my protons changing. I'm only seeing the number of protons changing, and usually what's happening is for every electron that's being released, we're gaining a proton essentially to balance out the nucleus. In this case, I know what number 7 on the periodic table is. It's going to be nitrogen. So I'm going to wind up with carbon 12 becoming nitrogen 12 and releasing 1 beta particle, or essentially 1 electron. Be aware of one thing in the data booklet. There is something in the data booklet that's there, and if it comes up on an exam, they will actually specifically tell you that that's what it is. There is something called a positron, which has the designation 0 + 1 E. It doesn't come up very often. It's not even in the textbook, for heaven's sake, but if they do mention a positron on a question, the positron is listed under your nuclear chemistry designations, and you would just have to plug it into your equation based on what you know about how to balance out your atomic numbers and your mass numbers. But like I said, there's a very slight chance you could see a positron show up on a unit exam, or more likely on a diploma exam. But just be aware that they exist, and if you see the word positron, don't panic. That's the designation for a positron, which is very similar to an electron, except it has a +1 as the designation there at the bottom, rather than it's essentially, yeah, you could argue that it's essentially a proton. A little different, but we're not going to get into that conversation today, because again, we don't really officially need to know. You just have to be able to identify a positron if you were to happen to see one. And again, the data booklet has the data for you on that. If you had to plug that in to an equation, they would just be asking you to know, do you know what's in your data booklet. That would be the reason why that kind of a question might pop up on an exam. All right, and that's beta decay. And then, oh, by the way, beta decay is a little bit more intense than alpha decay reactions. The radiation that it emanates is going to be blocked, but you're going to need a few thick pieces of paper and a few meters of air to actually stop this reaction. So it's still not that dangerous, but it does have a little bit more of the radiation has more of a kick to it, but it can still easily be stopped by most substances. Okay, so let's try Americanium-241 again, because we used that in the previous thing as well. Let's try to balance out a reaction where we have Americanium-241, and what would the products be in the beta decay reaction? See if you can figure that out at home. Pause me if you need to. I'm going to give you some information here in about 2 seconds once I very gently clean off my board. Ready? Okay, here we go. I'm going to start off with my reactant, which is going to be Americanium-241. There it is. I know it's got 241 as an isotope number or mass number, and I know that if I look on the periodic table, Americanium has an atomic number of 95. I know that in this reaction, I'm going to release an electron. So I have to balance out my equation now. Well, what plus 0 is going to equal 241? Well, that's still going to stay 241. And what plus -1 is going to give me 95? Well, it's going to be 96. So I'm going to have like 241 over 96. Now I got to go to my periodic table to find out what my element is that has an atomic number of 96. And it is going to be curium. Curium is going to be my element that's going to be released for isotope. So I'm going to release curium-241 as my product, as well as a beta particle. Again, all the details that I just gave you are going to be on this page right here, step by step. Look through it, walk through it. Hopefully it's starting to make a little bit of sense, because once you get the hang of these reactions, they're not that difficult to do. Last one, gamma reactions, gamma decay reactions. These ones are nasty, hence the name gamma, because they are releasing, in a lot of cases, gamma radiation. They're releasing photons. They're releasing electromagnetic energy in the form, generally speaking, of gamma rays. And we know the gamma rays back from the last unit, Unit C, they're ionizing forms of radiation that can basically damage and break up and physically chew apart DNA. Very nasty stuff. These decay reactions don't always involve a transmutation, though. If a gamma decay reaction occurs on its own, the element actually stays, the isotope stays the same. It doesn't change at all, because a photon or a gamma particle is essentially listed as a 0, 0 with the gamma symbol beside it. It doesn't have any neutrons or protons. It's electromagnetic radiation. It doesn't have protons and neutrons. However, gamma radiation or gamma decay reactions can occur in conjunction with beta and alpha decay reactions. So in some cases, you might see a question saying that, carbon-12 undergoes both alpha and gamma decay at the same time, balance out the equation. Well, then you would have to factor in the fact that we're releasing helium, but we're also going to be releasing gamma particles as well. And then we still have to balance out the equation. Now, the good news is the gamma symbol has a 0, 0, so it doesn't really factor in to balancing out the equation. But if a gamma reaction occurs on its own, a gamma decay reaction occurs on its own, you're not going to see the change of the isotope. The isotope will actually stay the same. It's not going to change at all. So how does that work? Well, in the case of, I've got an example up here on the board. I've got iodine 125. It's going to stay iodine 125, but also releasing gamma particles at the same time. How deadly and dangerous are gamma photons? Well, they can basically easily pass through a meter of aluminum or up to 30 centimeters of steel. So these are very, very powerful radioactive particles that can get through a lot of shielding to do some major damage, and they can do a lot of damage if they get inside of body tissues, obviously, because it's essentially gamma radiation is what we're dealing with here. Let's take a look at carbon and how carbon would play out in this reaction. I've got carbon-12 again, so here's my carbon-12, 6. There it is. I've got my gamma particle on the other side that's being released, which is 0, 0, gamma particle there. Well, what plus 0 is going to equal 12? Well, that's going to be 12. What plus 0 is going to equal 6? Well, that's going to be 6. So I'm going to be left with carbon 12 on the other side of the reaction as well. So the isotope doesn't change at all. If I were to say, hey, carbon 12 undergoes a gamma decay plus an alpha decay, well, then that's going to change things. Now I would have to add an alpha particle, which would be my 4,2 helium. Now I got to change my numbers up a bit. Well, now I've got 8 here that has to balance out the equation. I've got a 4 here that has to balance out the equation. This now brings me back to like the one on top there. That gives me my beryllium. So now I've got beryllium with the release of gamma particles and the release of alpha particles all at the same time. So you can combine reactions together, but you're still having to balance out the numbers on the bottom to the numbers on the top. So hopefully that kind of makes sense as far as balancing goes. Let's see if you learned anything from here today. Don't flip the slide if you haven't already. Don't look at it. I've got this written on the board pretty large here for you. Let's do a couple of practice questions and see if you can follow along at home. First one here is what I've got. I need you to figure out what this substance is here. I got the substance here that's listed as AZX. I want you to figure out what that isotope is based on the reaction that's there. And you know what? Name this type of decay reaction for me as well. See if you can actually name that decay reaction. Going to pause me if you need to. And here's the information you need in 2, 1. Here we go. We got helium being released. It's an alpha particle. So this is going to be alpha decay. So it's an alpha decay reaction based on what I see there. So what do? I'm going to take 222, subtract 4. That means my A value is going to be 218. I got 86 minus 2 is going to give me 84. So now that I know that my atomic number is 84, I know the isotope number is going to be 218, but 84 is the more important number. That's polonium. So I'm going to have polonium 218 being released from this alpha decay reaction. I'm actually on the wrong slide here. I thought I was on the actual slide here. There is another example. I kind of jumped ahead. I'm all over the place today. This example here does give you an example. I didn't really go over this officially, but if you want to go through this slide as well, there is another example there of a reaction. This one's talking about cobalt-60 that emits beta and gamma radiation. So in this case, we're having to factor in the fact that we're releasing an electron as well as the gamma particle. Everything is listed there in the notation section, so give that one a watch. The answer, just so you know, I won't even give you the answer. Just read that one on your own. That might be a good one to check out on your own. But going to the actual slide that I was going over, here we go. This is the slide right now. Now I'm on the right slide. Hooray for me. Yeah, it's going to be polonium-218, and it's going to have the atomic number of 84. A couple more coming your way. How about plutonium-244? It's going to decay and produce alpha and gamma radiation. In this case, I want you to write the entire equation down based on the word equation. So could you write down the entire equation for that word equation? Pause it out, see if you can do it. Going to come back in about 3, 2, 1. Here it is, plutonium-244. So the first thing I have to do is I got to find plutonium on my periodic table. You can tell I haven't planned this ahead of time. There it is, plutonium. It's 94. So I know plutonium-244 is going to have a number underneath of 94 based on the periodic table. I got Pu, there it is. I've got alpha particles being produced. So I've got a 2,4 helium, and I've got a gamma particle, which is going to be that really kind of weird symbol that looks like that. Now I've got the mystery isotope that I have to fill in the blank for. 244 minus 4 and 0 is going to give me 240. And 94 minus 2 and 0 is going to give me 92. So 92 on my periodic table is going to be uranium. So I'm going to produce uranium-240 as part of this reaction. There it is. Hooray for us. It worked. One more word equation. I got radium-228 that undergoes beta decay. See if you can balance out and write that word equation down, or sorry, the actual a chemical equation down for that with using nuclear notation. In 3, pause me if you need to, 2, 1, go. Here we go. I got radium 228. So radium 228, I'm going to write my isotope number on the top. Radium is, other than a place where there's hot springs, I can never find radium on these periodic tables. Radium is, how long of a video can I make just by not knowing where radium is? Radium, 88. And it's Ra. And I've got beta decay, so I got electrons being released now. So I have to write down my electron. There's my beta particle. So what minus 228 minus 0 is going to give me 228. 88 minus negative 1 is going to give me 89. So I do have a transmutation. I'm going to go up 1 in the periodic table. I'm going to have actinium. Actinium? Actinium. Actinium. I don't know. AC. That's what we're going to wind up with. Those are all of your decay reactions. If what I said made no sense, and that does happen from time to time, give this video a watch. Crash Course is going to walk you through this in 10 minutes. If you feel like you need to go one more time through it and have nicer and cooler graphics than my little crappy little whiteboard, please give that video a watch. It's definitely worth your time to do so. Going to finish up today's discussion with one more thing. How do we detect these particles of radiation that are being released? Well, we first of all, we have to, if we do have radioactive, if we have radioactive decay going on, obviously we have to have safety is of paramount concern, because if we're using these reactions to make power, obviously if we're producing gamma radiation as part of some of the byproducts, that's something that we don't want to expose humans to. I think most of you would probably be familiar with the fact that we don't want nuclear power plants, leaking or having issues. Heaven forbid, Chernobyl or Fukushima or Three Mile Island. These are all examples of where nuclear power plants have basically protocols have been breached. Safety protocols were breached, and we had radiation that was released into the surrounding area. In large or small quantities, depending on what the size of the radiation leak was. But how do you measure how much of this radiation is going around? You use something called a Geiger counter. And Geiger counters are essentially there. The closer you get to the source of the radiation leak, they're going to basically take in more either charged particles or photons or beta particles or whatever. They're designed to measure these particular particles that are either being released, the alpha particles, the beta particles, especially the gamma particles. And the more of them that are being trapped inside these devices, the higher the count is, the radiation count on the Geiger counter. If you want to see how a Geiger counter works, watch this video and that will explain it for you. And that, ladies and gentlemen, is my first of 2 topic discussions about harvesting nuclear energy. Join me next time where I discuss the practical application of these radioactive decay reactions and how they pertain to producing electricity for you and I. No homework for today. The homework will be coming after the second part of this discussion, and then you'll get all your questions then. So don't worry about doing them quite yet until you watch the part 2 video. Until then, thanks for tuning in, folks, and we will see you very soon.